All right, so in our parent course this week, we're talking about set theory. We're going to be working in set theory throughout chapter 2. And in the very first section that we covered in that class, one of the things we talked about were sets of numbers. This is something that you would have talked about probably as far back as pre-algebra. You would have maybe recapped on it in algebra as well. But this table appeared in the lecture notes for section 2.1 in our parent class. And what I wanted to do here is just go into a little bit more depth on this, get a little bit more practice working with this, just so you have a familiarity with what these sets of numbers are and how they compare to each other. So since we already talked about this in the parent class, I'm not going to go through this table as intentionally as I did there, but just a quick recap. We have different sets of numbers which are given specific symbols shown here. The only exception is the irrational numbers. We're not going to use a specific symbol for that. But natural numbers is at the top of our table here, and those are the counting numbers, 1, 2, 3, 4, and so on. It goes on forever. The whole numbers are almost the exact same as the natural numbers, except they include 0, whereas we didn't have a 0 here. The integers include all positive and negative whole numbers as well as 0. So it contains everything that the whole numbers contained, but it also has negatives of all of these values. The rational numbers, excuse me, are the set of all numbers that can be written as a quotient of one integer over another. So you can write it as a fraction where your numerator and denominator are both integers. Okay? Real numbers are the set of all numbers that can be expressed as a decimal. Now, this is the definition I believe that your book gives. It's not really the way a mathematician would define the set of real numbers, but it works for what we're trying to do. Irrational numbers are numbers that are real numbers that are not rational. So irrational literally just means not rational. Okay? Now, what some people like to do is show the relationship between these sets using kind of a diagram. And I'm going to use a diagram to do that. Okay, I'm going to create a little rectangle, split that in half. And, excuse me, this rectangle is going to represent, the whole thing is going to represent the set of all real numbers. Over here, I'm going to put the irrational numbers. Okay? And over here is going to be the rational numbers. And I'm going to use Q for that. So these are the rational. So basically, this diagram is saying that all of the irrational numbers, I'm going to think of them as being over here. All of the rational numbers, I'm going to think of as being over here. And together, the rationals and the irrationals form the set of real numbers. So every real number is either irrational or rational, but no number can be both at the same time. They're mutually exclusive. Now, within the set of rational numbers, we have these other three sets of numbers. It turns out that every integer is also a rational number. So I can do something like this. I'm going to call this z, because this is going to represent the set of integers. Notice that the integers are completely contained in the set of rational numbers. So in other words, every integer is also rational, but not every rational number is also an integer. Okay? In a minute, I'm going to start writing some examples in these sets. Within the set of integers is also the set of whole numbers, because every whole number, as we can see in this set, the way that we've listed it out here, also belongs to the set of integers. So every number that's in this set of whole numbers is also going to be inside the set of integers. And then the natural numbers are contained in the set of whole numbers. So let's get some examples that we can write in here. Starting with natural numbers, things like 1, 2, 13, a billion. You know, there's lots we can put in here, but I don't have enough space to write much more. The whole numbers include all of the natural numbers, but they also include the number 0, which is not found in the set of natural numbers. That's the only thing, the only number that I could put outside this small set, which is not small really, it's an infinite set, but the set of natural numbers, but inside the set of whole numbers. The integers contain all of these numbers as well, including the negatives. So -4, -103, -6, those kinds of numbers. Okay? Now the rational numbers contain all of these. And to see why an integer or a whole number or a natural number is also rational, all we have to do is something like this. Take the number 3, for example. The number 3 is a natural number, right? And clearly it's also a whole number, and it's also an integer. You can actually see it written in all 3 of these sets. But is it rational? Well, it is rational because I can take the number 3 and write it as 3 over 1. That makes it a rational number because it's written in the form of a quotient, one number over another, or one integer over another. Excuse me. I'm going to apologize in advance for any coughing that I do. I'm kind of getting over a cough right now, so you might hear a bit of that. Okay. The fact that I can take an integer, like the number 3, and write it as a fraction just by putting it over 1 is what makes it rational. So all of the numbers that are in these sets here, I could do the same thing. I could put each one of them over a 1, and that way I can see that they're all rational as well. But there are numbers that are rational that belong to this set that we're calling Q that don't belong to any of these sets. For example, 1/2. That's a rational number, but it's not an integer, so it's also not a whole number or a natural number. 31s, we call it that. That belongs outside of the set Z here of integers, but inside the set of rational numbers. In fact, numbers that have a decimal representation can also be rational. So for example, 0.159 is a rational number. Why is that a rational number? Well, remember, excuse me, the rational numbers don't have to look like a fraction right away. The definition of rational numbers simply implies that a number is rational if it can be written as a fraction with integer numerator and denominator. So the number 0.159, how do we write that as a fraction? Well, if you remember place value, this is the tenths, hundredths, thousandths place. This is the same thing as 159 thousandths. 0.159 is literally the same thing as 159 over 1,000. So I could write that as a decimal, or as a fraction. That makes it rational. And in fact, there's nothing special about this specific number. Any decimal that terminates, which means it has a finite number of digits, will always be able to be turned into a fraction using the place value of the rightmost digit. But we know from practice that there are numbers that can be written in decimal form that do not terminate. For example, 0.131313 ... right? That is a number. The ... here implies that it's a non-terminating decimal, but it also implies that there is a pattern of repeating digits here. 13131313 on forever. This turns out to also be a rational number, even though it doesn't have a rightmost digit, which I needed in this example to create a fraction. In fact, any decimal number that has a repeating pattern is rational. Now, I'm going to show you with this one example how to prove that this is rational. And this is more just kind of understanding the concept. You've probably been told before that decimal numbers with repeating patterns of digits are rational, but it may not have been explained to you why that's the case. So to see why, we're going to let x equal 0.131313 on forever and ever and ever. So what I'm doing is I'm going to use kind of an algebraic trick to try to put this in the form of a fraction. The next thing I'm going to do is take note of how many digits are repeating here. There's 2 total, 1, 3, 1, 3, 1, 3. If I were to multiply both sides of this expression or this equation here by 100, remember, when you multiply by a power of 10, a decimal number, if you multiply by a power of 10, all that does is move the decimal point around. Multiplying by 100 will move the decimal point 2 spots to the right. That makes this 13.131313, and so on and so forth. Now, even though the decimal place has moved, there are still the same number of digits after this decimal point as there are here. That would not be the case if this had a finite representation, if there was a finite number of digits here. But because it's infinite, I still have an infinite number of 131313s appearing here as I do here. So everything after the decimal point here is identical to everything after the decimal point here. And this is where the next trick comes in. I want to subtract all of the stuff after that decimal point away. In other words, I want to subtract 0.13131313 from both sides so that this side just becomes 13. Okay? But if I were to do that, that's the same thing as subtracting both sides by x, because x is equal to that. So I could write 100x minus x. I'm subtracting x from both sides, but using the fact that x is equal to 0.131313 on and on and on forever to just simply subtract away that decimal. This becomes 13. Okay? Now on this side, I can combine like terms. 100x minus x is 99x. And then finally, divide both sides by 99, and I get that x is equal to 13 over 99. But wait a minute. We already gave a definition for x. X was equal to this repeating decimal, 0.131313 on forever. I also showed that the exact same x is equal to 13 over 99. So in other words, this repeating decimal, non-terminating repeating decimal, is equal to a fraction. And we could go through a similar process for literally any decimal that has a repeating pattern, even if that repeating pattern does not start until a ways down the line. We're not going to go do more examples of it because that was just to get you a sense of the concept. Okay? Let's look at irrational numbers now. An irrational number is a decimal number, is a real number, something that can be written in the form of a decimal, but it is not able to be written as a fraction. It is not rational. Irrational numbers don't usually come to mind as often because at this level you will not have worked with them quite as much as rational numbers. So instead, I'm just going to give you some classic examples of irrational numbers. The number pi, for example, is an irrational number. And we don't have enough background in this class to prove that. You kind of have to take my word for it. But the number pi is equal to 3.14159, blah, 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 blah. It has a non-terminating decimal representation, but it does not have any kind of repeating pattern. And that's something that characterizes irrational numbers when written in decimal form. They will always have a non-terminating decimal expansion, which means they have an infinite number of digits after that decimal point, and there is never any repeating pattern that occurs like there is here. Okay? Other irrational numbers that we come across frequently are ones that occur from radicals. So for example, the square root of 2 is irrational. And we could actually prove that one, but for the sake of time, we're not going to do that. Square root of 5 is also irrational. In fact, if you take the square root of any integer that is not a perfect square, then it's automatically going to be irrational. And again, we're not going to prove that here. It's a little bit beyond the scope of this class. But these are some examples. If the square root of 101, for example. So most of our examples of irrational numbers that are accessible to us at this level are going to be of the form of some square root where the number in here is not a perfect square. Okay? All right. So let's get into a little bit more here. What I'm going to do is, let's see. I'll write this down. List all sets that the given numbers belong to. Okay? So we'll do maybe like 3 examples here. So the first example is going to be the number negative 12. Okay? I want to determine which sets this number belongs to. So coming over here, where would negative 12 belong? Negative 12 is not a natural number because it's not positive. In fact, it's negative, so it couldn't be a whole number either. Notice the whole numbers don't contain any negative numbers. The integers do include negative numbers, and negative 12 is like a negative whole number. So this is, in fact, an integer. I'm going to use the set notation to write this, to make this a little bit more concise. But because it's an integer, that automatically means that it's a rational number as well, because every integer is automatically rational. So I'm going to include the set of rational numbers. And then similarly, every rational number is also a real number. So this is also going to be a real number. Okay? What about the number, let's say, 5.136, and I'm going to put a line over that. So that bar right there over the 136 indicates that we have a non-terminating decimal, but with a repeating pattern. So this is 5.136, 136, 136, 136, on forever. We just showed that numbers that have a non-terminating decimal representation, that have a repeating pattern, are always going to be rational. So I know that this belongs to the set Q, which means it also belongs to the set R, since every rational number is also real. Does it belong to any of these other sets? Well, no, because as soon as we get from Q down into one of these smaller sets, all of these numbers don't have decimal points in them because they are whole numbers, whether positive or negative or zero. But no fractions, no decimals or things of that nature. So it's not going to belong to any of those sets, and it's certainly not going to be irrational because it's rational. Okay, as a final example, what about the square root of 91? Well, the square root of 91 is going to be irrational. 91 is not a perfect square. It doesn't have a nice square root of something like 4 or 9. Those are perfect squares. 91 is not a perfect square, so it is irrational. Okay? Remember, we don't have a symbol for the irrational numbers. Okay? I'm going to do a similar type of example, but this one's going to include some true-false statements. So true or false. And this time what I want to do is kind of practice using set notation, specifically the element of symbol. So let's do a few more of these. A, B, C, D. Okay. Is this true or false? 3/10 is an element of Z. So this is saying, is the number 3/10 an element of the integers? Or in other words, is 3/10 an integer? In which case I would say that no, that's not true, because integers are positive or negative, whole numbers or zero. This is not a whole number, it's a proper fraction. So for this one I would say false. Okay, let's try another one. Pi, is that an element of the real numbers? Well, pi we've listed over here as one of our irrational numbers, but whether irrational or rational, any number belonging to either of these sets are automatically going to be real. So yes, this one would definitely be a real number, true. All right, what else do we have here? -7 is an element of the natural numbers. Is this true or false? Well, natural numbers look like whole numbers, but only the positive ones. It does not include any negative whole numbers. So this would not be true. This is false. Okay? All right. And then finally, is it true that 13.741 is an element of the rational numbers? Well, yes, this one is also true because, as we showed over here, any decimal, any number written in decimal form that has a non-terminating decimal representation, finite number of digits, can always be written as a fraction, which makes it rational. So this one is definitely going to be true. Okay? I think that's everything I wanted to cover for this first lecture. So this first week is going to be very, very straightforward. There's not a whole lot that we need to do. It's just getting familiar working with these sets. Okay? Starting next week, we'll probably be getting a little bit more in-depth with some of the set theory stuff. But that's going to end this first lecture.